Good morning, students. We are going to see the recap of Unit 3, Part 2. So, in the morning section, the previous section, what we have seen is a supervised learning. So, with the continuation of that, we are going to see the recap of unsupervised learning. So, is a unlabeled data. That means the input and output, there is no coherence. So, we may not be aware of how it has been correlated. Okay, unsupervised learning is a type of machine learning where the algorithm learns from the unlabeled data. So, unlike the supervised learning where the model is trained on input and output pairs, unsupervised learning tries to find the hidden pattern or intrinsic structures. So, is a coming under the label data where the dependent variable and independent variable have not do not have correlation. We need to learn from the data how it has been correlated. So unsupervised learning try to find the hidden patterns or intrinsic structures in the input data without any predefined labels or outcomes. So this is whenever the people say is unsupervised learning, so the first thing that's supposed to come to our mind is a unlabeled data. And coming to the unsupervised learning, there are four types that we have seen, okay, during the content delivery. Okay, since this is a recap, I quickly go through the 4 points: the clustering, dimensionality reduction, anomaly detection, and association rule learning. Okay, so clustering, there are different types of clustering is there that we will see further. Okay, clustering, in clustering we have a k-mean clustering, divide data into k number of clusters. So minimize the intra-cluster variance. Example, grouping chemical sample based on the composition. Whereas in the hierarchical clustering, we have a dendrogram. So dendrogram of clusters, build a tree dendrogram of clusters. So it will form a one single, or what you call the single cluster. So the dendrogram starting, merging and repeating. Starting with each data as its own cluster, merging the closest pairs of clusters step by step, so that the finally repeating this process until all the data points from a form a single cluster. So you could be able to see from the figure the neighbor data has been clustered and finally it has been clustered as a one single unit. Okay, so repeating this process until all data points form a single cluster. And under the clustering we have a DB scan, that is a density based spatial clustering of application with noise, groups together the data points that are close in density. Okay, so the very good example, detecting the outliers in sensor data from chemical reactors. So in that case we can go for this type of clustering. So the second point in unsupervised learning is a dimensionality reduction. So whenever the word dimensionality reduction, the first point we will see the principal component analysis. That's come to our mind. The project data into a lower dimensional space using a linear combination of features. The very good example that in chemical engineering perspective, we will collect the different types of spectra, either from a NMR data, okay, or a Fourier transform infrared spectroscopy, or a XRD, TGA. Okay, so analyzing the FTIR spectra or NMR data for chemical fingerprinting. So that will help you to understand the how the compounds has been functional group, how it FTIR functional group. Okay, and if you have XRD, how the elements has been arranged in the order. Okay, this all whether it's a crystality or a amorphous substance that can be determined by XRD. Okay, so when you have principal component analysis, will help you. Okay, that means lower the dimensional space using a linear combination, so that will analyze the spectra. So these are the things actually in application oriented with respect to chemical engineering. And TSNE, T distributed stochastic neighbor embedding, external for visualizing high dimensional data in 2-dimensional or 3-dimensional. Example, visualizing the clustering of chemical process performance data. Autoencoders, neural network that learn to encode and decode the data. So encode and decode the data, that learn to encode and decode the data, used for noise reduction, mainly used for reconstructing the corrupted process signals. So encode and decode the data, neural networks. Okay, so when you see this type of unsupervised learning may be applicable for different techniques. I mean, under which you have a different techniques. Okay, and for unsupervised, broadly classified into four types. Okay, one is clustering, dimensionality reduction, anomaly detection. Okay, and so on and so forth. So, and under the anomaly detection, the isolation for us support one class support vector machine and statistical thresholding. Identify the rare items, events, or observations which raise suspicions by differing significantly from the majority of the data. So the example is detecting faults or malfunction in process control system based on the sensor data. So association rule mining. The fourth one is the associating rule mining. As I told you in the lecture, if one happens, the second one is likely to happen. Okay, if both happens, or how would be the what would be the effect? Okay, so in a pilot plant, identify the rules such as if the pressure increases, high pressure, the temperature also tend to increase most of the process. Okay, so association rule mining. So we have clustering, we have dividing the technique. Okay, four different types, under which we have a clustering, k-mean clustering, hierarchical clustering, under which dimensional reduction, we have PCA, DB scan, autoencoders, and the fourth one is association rules. Okay, so when you see the anomaly detection, support vector machine, as well as the statistical thresholding, which is missing over here. So what are the application in terms of chemical engineering, which we have seen in the elaborately, okay, during the lecture. So I just would like to show you what are the techniques, what are the methods are available in the thing, under which what are the techniques which are available in the unsupervised learning. Okay, so the advantages of unsupervised learning: no need for the label data, even if it is there is no correlation between the variables, that is a dependent variable and independent variable. We can go for a unsupervised learning techniques to determine to find the group the data, and then later we will do the algorithm. Okay, so the limitations are to evaluate the results objectively, no ground truth. Okay, or to evaluate the results objectively. Okay, no ground truth. Results can be sensitive to parameter tuning, may produce misleading patterns without domain knowledge. So k-mean clustering. So we will see examples for k-mean clustering. So catalyst performs classification. Scenario: you have experimental data from multiple catalysts tested under similar reaction conditions. Okay, so they cluster the catalyst based on the features like conversion, efficiency, selectivity, and stability to identify the high performing groups. So the example is the second one is batch process monitoring. The scenario: analyzing the historical data from multiple batch runs in a reactor. So they mean clustering. Cluster the batches based on the key parameters like temperature, pressure, pH, yield to identify the typical operation pattern versus deviation. So the k-mean clustering, the clustering is the data validation, analyzing the historical data from the multiple data batch runs in a reactor. Okay, that is a scenario. So cluster the batches based on the key parameters to identify the typical operation pattern. Okay, so that's the thing. And coming to the hierarchical clustering, okay, classification of chemical based on properties. Scenario: grouping a database of chemicals based on the physical and thermodynamic properties. Okay, so create a dendrogram to visualize the similarities and classify the substance into families and then make it into a single cluster. Okay, so this type of thing can be classified under the hierarchical clustering, this type of data. Okay, so heat exchanger fouling pattern. Monitoring the fouling tendency across the multiple heat exchanger. As you know, the heat exchanger have a fouling tendencies. Okay, when you have a what do you call it? The fluid which is having a fouling characteristic, we allow to pass and then trying to change the heat transfer the heat between the fluids. Okay, so we will have a fouling part will be there. Okay, this is not unavoidable. This is unavailable. Okay, unavoidable. Okay, use of hierarchical clustering. Group heat exchangers with similar fouling behaviors based on the time series. Okay, temperature drop and pressure data. Okay, so with that we can go for a hierarchical clustering by collecting the data from the temperature drop and the pressure data. Okay, so coming to the DB scan, anomaly detection in sensor data. So continuous monitoring of reactor temperature and pressure via IoT sensors. Okay, now IoT sensors will monitor the temperature and pressure. So in that case, DB distributed, density based spatial clustering. Identify normal operating condition versus outliers. That means deviation from the normal data, indicating the abnormal or hazardous behavior. And similarly, example DB scan. Okay, the density based spatial clustering. Okay, for the second case like particle distribution pattern from simulation data. And principal component analysis is a dimensionality reduction. So where you have a spectroscopic data analysis, so you have hundreds of spectral intensity readings across the many wavelength for a set of stimuli samples. So reduce the dimensionality of the spectral data while retaining the most of the variation. So identify the sample grouping, detect outliers, and simply find the classification task. So principal component analysis, another example, process variable compression, a chemical process with 30 to 40 sensors, okay, generate the large data sets, temperature, flow rate, pressure, pH, okay, and so on and so forth. So the principal component analysis reduces the number of variables to a few principal components that capture the most significant variation, helping with the visualization, monitoring, and early fault detection. Okay, so they are under the unsupervised learning. You have four categories, and under that you have a distribution. Different types of techniques are available. So which one is best suited for our case, that can be studied. So coming to the TSNE, distributed stochastic neighbor embedding. So similarly, the cases which have been explained already clearly. Okay, autoencoders is a noise reduction in sensor data. So the real-time data from chemical plant sensors often contains noise. Even when I try to record the video for the blended learning, obviously the noise may occur. Today morning when I try to take the video, actually the noise occurs because there is some ad came. Okay, they're just shouting on the road. Okay, with the mic. So obviously that noise I couldn't able to block it. Okay, so obviously what I did is that I just bring the what you called mic very close to me, and then try to make sure that the noise is not hearing on the other side while recording the video. So the like that. So the real-time data from chemical plant sensors often contains noise. Use of autoencoders, train an autoencoder to learn the compressed clean version of the signal and reconstruct it effectively, filtering out the noise. Okay. So even in the speaker, if you see there is a noise thing, even a auto mic. Okay. So you see the option in the speaker, so they have a noise clearing effect is there. Okay, when you click on it, so obviously the small noise or the noise, it will filter automatically. Okay, so autoencoders, latent feature extraction of for reaction monitoring, high frequency time series data from a reaction process. So use of autoencoders for this scenario is extract meaningful latent features that summarizes the system dynamics for use in predictive modeling or anomaly detection. Okay, so this type of things we will go for a autoencoders. So isolation forest. So this one is a forest and a support vector machine or the coming under the category of which category? Can you please tell me which category it belongs to? Support vector machine and thing is on the third technique. What is the third technique actually we used to say? Okay, so if we see here, go back to the previous things and try to say, understand the techniques which has been used actually, the clustering, okay, as well as the anomaly detection, association, rule mining, and dimensionality detection. So these are the four types which are coming under the goals of unsupervised, key goals of the unsupervised learning. Okay. So coming to the hierarchical testing, this is all explained already. So we will go back to the, after this we will go for the model evaluation and validation. So support vector machine already explained to you, okay, in a extensive way. So the what do you call a priori algorithm. One goes, the other one may happen. Okay, so let's say find rules such as high agitation speed, low pH. Okay, then the product failure may happen, and with the high confidence we can say it may lead to the product failure. So in that case, we can go for a priori algorithm. Okay, and coming to the here, the second case, pressure high, flow low. Okay, and the shutdown triggered. So there is a chances of shutdown trigger. Enables preventive control action to break the chain supply. So FP growth similarly is coming under the techniques. Okay, FP growth is a efficient algorithm for mining the frequent item sets without candidate generation. Okay, so what is model evaluation? After we do all of this, learn the what is called supervised learning and supervised learning. The model evaluation and validation is an important thing. So, how to validate the model? Okay, so when we build a machine learning model, we want to measure how well it performs, not just on the data we used to train it, but more importantly on the new unseen data. Underline the word new unseen data. So in the supervised learning, okay, we have a relation between the variables, label data, but in unsupervised learning is very difficult. We could not able to know the relationship. Okay, that's why we will need to know the patterns how it has been correlated. Right? When we build a machine learning model, we want to measure how well it performs, whether it's underfitting or overfitting, okay, and so on and so forth. Okay, not just on the data we used to train it, but more importantly, a new unseen data. That's where the evaluation and validation techniques comes in. So we have for that we will classify it based on the regression model or classification model, and which one is better, which one is the model is best suited or not. Okay, that can be determined by the data. Okay, the mean absolute error, mean squared error, root mean square error. Okay, and the coefficient of determination R square. How well the model is placed. So these values will help you to identify whether the model is good or not, as perfectly fitting or not. If not so, what are the possible causes why it's not fitting? That can be analyzed by the regression models. Okay, when you go for a classification models, again we have a different types. Then we will go one by one for that later. Okay, that we already explained also. In fact, okay, so please try to understand what is mean absolute error. So how is this need to be calculated, and what is mean square error? How this need to be calculated, and what are the units, and which category we need to go for mean square error, which category we need to go for what you call mean absolute error, and when we need to go for root mean square error. This all is supposed to do. So each category has been the formula has been given here, as well as the cases have been explained in the main class. Okay, so this is a recap. So why I'm giving a recap is that so that you can see the overview of the content which has been delivered for the unit 3. Okay, so part by part, if you see, we may not getting a real picture of the things. So if possible, I will try to take at the last unit 5 the overall of what has been covered so far in all the 5 units. So you understand what is the essence you need to take when the problem arises. What are the techniques? Actually, what I am not going into very depth of the very depth actually. In fact, okay, because even myself is a new learner for this data analytics and machine learning in chemical engineering. Okay, so some of the terms even I'm not referred to as a usually we engineers when you people come into engineering chemical engineering, there are a lot of technical jargons will be there for them for you to take minimum 1 or 2 years to understand the jargon itself. Similarly, the in data analytics and machine learning is despite they say what you call the origin of computer science. Okay, but is an application oriented in chemical engineering. So we should know the theory behind it and where we need to apply that also we supposed to know, because the other people on the other side of the engineering may not be knowing what are the domain knowledge. Without knowing the domain knowledge, it's very difficult to understand where it is needed, that particular technique. They may be knowing the theory behind it. Okay, so we need to identify. So this is a theory. So we need to identify with the domain knowledge is knowledge. Okay, where we need to apply this particular technique. Okay, or how to clustering the things, how to data, whether it's a supervised data or unsupervised data. Okay, it's a labeled data or supervised learning or unsupervised learning, labeled data or unlabeled data. Okay. So what I'm trying to say. So I just try to give you a broad perspective. Okay, in the during the recap section, so that you will understand better. Okay, about the whole process of the particular unit, why it has been given to you that particular unit, and when you need to apply and how to apply the chemical engineering principle with the chemical engineering principles. Okay, that is a very important thing. Coming to the chemical engineering examples, so here the R square is 0.92. This model is very well fit, right? So when you see here, it has been the output is equal to the input variable function of input variables, where most of the input variables have a positive effect of the thing, and there may be chances. Okay, we may not say actually 92% or 98% is a good fit. Okay, so that the model fits well when compared to the other things. So if it is 0.5, so you may be missing some of the data, which even the variables. Okay, I said dependent variable, independent variables. So because of that, the R square value may comes down. So if you see here 0.67, okay, so the model explains 67% of the energy consumption. But however, this is decent, but suggests that there are other factors may be contributed to the data. So when you add that ambient temperature and fouling for this particular scenario, obviously the R square value may increase. Okay, or this having a other effect. Okay, so that's why we have seen what is the quadratic effect, or what you call polynomial effect or what you call the exponential. So you know the equations, how the nonlinear equation comes, right? So the independent variable is equal to function of independent variable is equal to the, dependent variable. That is, output is equal to function of few inputs. Okay, so few input variable. So that is how the model equation comes, right? So in the value of r square root mean square, I mean, so r square value, we can determine how whether the model really analyze can able to accept the data, all the data which has been given to, or the any other variables which are missing that can be found out. Okay, can be find easily. Okay, only 35% of the variation in COD is explained. The model is weak, so possibly due to the missing important variables like microbial activity, oxygen transfer rate, or measurement noise. Okay, coming to the significance of R square, whether which one we need to. Obviously, I have R square, low R square, which indicates need for more data, better features, or more suitable model. R square alone is not everything. Always combined with the residual analysis, root mean square error, okay, mean absolute error, and domain knowledge. So here we have already discussed enough. Okay, whether which type of error, absolute. Okay, error type is absolute or squared or root of mean square error or relative. Okay, so here the outliers, the anomalies has been accepted, penalizes outliers whether it's yes or no. Okay, so the unit may change or unit may not change along this different techniques, regression models techniques. Okay, where we can find out the errors. Okay, so for squared units, when you have a mean square error, the unit may change to squared units. Otherwise, for other cases of mean absolute error and root mean square error, we have the same unit. So when they closer to 1, that means it's a good fit, good value. Lower value of MAE, MSE, and RMSE will give you a better fit. I mean, equation is really good. Okay, for classification models, we have accuracy, precision, recall, F1 square, confusion. Okay, F1 square, confusion matrix, and ROC curve and area under the curve. Okay, so when you see here, the ROC curve is nothing but a receiver operating characteristic curve. When you see here the x-axis and the y-axis, you have a false positive rate and a false true positive rate, and this can be calculated by means of the false positive or true negative, or true positive or true negative. So when you go back to this slide, so we have I have explained during when I taught you this content. Okay, I told you about what corona scenario, right? So actual positive and predicted positive, if both are correct, okay, then is a true positive. If this is contradiction, okay, the actual positive and predicted or predict actual positive, and you have a what you call false positive, sorry, actual negative, actual positive and predicted negative, you have a false negative. Okay, so in that case actually is positive but predicted as negative. Okay, so this all will help you to analyze the things. So area under the curve is a perfect classifier. So how to understand actually classifiers, regression models as well as the for classification models. Okay, so these are the identifiers which will help you to say whether it's fitting the data is really fitting the model or not. That will help you how good the model it is. Okay, that I can put it in that way. Okay, and coming to the model validation techniques, we have a train test split. So usually 80% training and 20% testing, class validation, k-fold class validation. So when we need to go for k-fold class variation, that I already told you. Okay, so during the lecture, leave one out class validation and satisfied k-fold class validation and bootstrap validation. So the case has been given here, which are simple. The first one is very simple, whereas in the last one, if you see, may not reflect the real world test cases. Bootstrap validation is good for uncertainty estimation. Okay, good for uncertainty estimation. So sensor readings, all of this we can put for the bootstrap validation. So the example has been given for here, train test split, and 1800 samples have been trained, and 200 samples have been tested, and k-fold class validation, we will take one part as a testing and the remaining parts as training, and do it for repeatedly, do for the other things. And leave out one class validation, the data point is very less, as I told you, okay, during the lecture. So if the data is very less, then we can take out one point, okay, and then try to find as a cluster, and then we just do it for the this one. Instead of cluster, you just do it for each and every point. Okay, and a certified k-fold class value validation. If only 10% of the batches are failed, okay, a normal k-fold might result in some folds having geo-fail. Okay, so that is a main advantage. I mean, essentially when working with the imbalanced data set, whereas in the bootstrap validation provides robust confidence intervals and is helpful in assessing the model reliability under varying environmental conditions. So this will give you a confidence intervals. So that is very important. Train the multiple models. Test on the out of back data each time. Average matrix. Okay, mean absolute error, aspire, and look at the standard deviation. Okay. So when you see here, chemical engineering for especially the fourth and fifth case. Okay. So batch quality classification in pharma is a very good example. Okay, keeps class proportion for better classification, whereas in the bootstrap good to uncertainty called quantification. Okay, so corrosion rate modeling under uncertain environment, you may not be knowing actually the environment, whether is a fouling tendency errors occurs or corrosion occurs. Okay, that depend on the type of fluid which has been happened for the corrosion, or the environmental condition that leads to a what you call the uncertainty. Okay, so the corrosion rate maybe depends on the uncertainty of environment. Okay, and environment the place where it has been kept, the material has been kept. Okay, so when you see the chemical engineering examples for validation, imagine we are building a predictive model for catalytic activity. Okay, predictive model for catalyst activity or reaction yield based on the temperature, pressure, and reactant concentration. So we need to make sure the model is not just fitting noise. It can generalize to new experimental condition. It won't mislead the process optimization decision. Okay. So with this note, I just try to recap the second unit, third unit. Okay, with the overall of what is the supervised, unsupervised learning, what is the unlabeled data, what are the different types of clustering that are available, anomaly detection, dimensionality detection, okay, as well as a priori algorithm. Okay, so and also we have seen actually how to validate the model, how to evaluate the model. Okay, so with this note I stop it here. I believe that you have a good idea about unit 3. If you have any doubt, just knock me, even in WhatsApp also. Okay, I'm very well reply back at the earliest. Okay, so hope you understood. Please start to prepare for your FAT 2. Okay, especially for your next assessment, and the syllabus. I'll let you know actually the syllabus, what the date has been announced for what you call this particular assessment for honors and minors. Okay, with this note, I stop it here. We will continue with the fourth unit shortly, because we need to complete the fourth and fifth unit before the April 30th. That is the deadline has been given for us. Okay, so we will. I will keep on posting you. Okay, and we are, as you know, we are having a international conference which is going to be held on 21st and 22nd. Hopefully, I will be little free after that. Okay, and meanwhile, I will try to complete a few part of the unit 4 as well, so that you can also start preparing parallelly for the your FAT. Okay, so since the date has not been announced, but we just try to start, because the third unit I already completed. So with this note, I just wind up this section, unit 3 recap. Okay, the second part, and see you in next class. Thank you for your kind attention.